Think it's recording?
Yes.
Is that okay? Do you think it's... All right. So here we go, 6.1, exploring the graphs of polynomial functions. We're going to cover 4 types of polynomial functions in these notes. We reviewed yesterday linear functions and a bit of quadratic, and we'll do a little bit more today. So it says here, and the first page is just information. It says a polynomial function in one variable is a function that contains only the operations of multiplication and addition with real number coefficients, whole number exponents, and 2 variables.
What does any of that mean?
It means that in a polynomial function will be in the form of y equals something's happening to x. That's what it means. The degree of the function is the greatest exponent of the function. We covered degree in Math 9 and Math 10 and a bit in Math 11 as well. So for example, f of x equals 6x cubed plus 3x squared minus 4x plus 9 is a polynomial function of degree 3 because 3 is the highest exponent that the equation has. And more specifically, it's a cubic function because it has degree 3. Okay, so linear functions have degree 1 because we have an invisible 1 on the exponent, on the variable. We have quadratic, which has a highest exponent of 2 or squared, and then we have cubic, which looks like a cube. Okay, reminder that we have 4 quadrants on the coordinate plane here on a graph. So we go counterclockwise. This is coordinate 1, 2 there, 3, and 4. So today I'm going to ask you about graphs and what is their start behavior and their end behavior. And what I mean by that is what quadrant do they start in, what quadrant do they end in. So that's what that means. That would be a good thing to put in your foldable so that you could remember which quadrant was what. Although, if you remember, we start here in the one where x is positive and y is positive and go counterclockwise. It's not that hard to remember. It says the graphs of polynomial functions of the same degree have common characteristics. And the end behavior of a graph is the description of the shape of the graph from left to right. So we talked about that yesterday as you read a graph like a book from left to right. Cartesian grids are divided into 4 quadrants by the x-axis and y-axis. That was this that I just talked about. Any point where the graph of a function changes from increasing to decreasing or from decreasing to increasing is called a turning point. So that sort of makes sense. Wherever the graph changes direction is a turning point. Talked about domain and range yesterday. The domain is the set of all the x values of the graph, while the range of the function is the set of all y values. And remember, it's all possible things, digits, numbers, values, x and y can be, is an easier way to think of it. The x-intercepts are where the graph crosses the x-axis, and the y-intercepts are where the graph crosses the y-axis. Okay, so let's go through 4 types of graphs. We're going to graph them and talk about their behavior. And just so we can have 2 different ones, let's change the second one to x. So we'll have y equals 2 and x equals negative 1. There's no point in graphing 2 graphs that are exactly the same. So this one doesn't have, y only has 1 variable, it's just y equals 2, or the second one, x equals negative 1, they only consist of 1 variable. We call those constant function type, and they are degree 0. There is no variable to have an exponent on. So let's graph both y equals 2 and x equals negative 1 on this graph. If you graph on a test freehand, I will deduct marks. Graphing is precise, and because it's precise, it needs to be drawn with straight edges. So get yourself a ruler, use the edge of your textbook, use your calculator, case, whatever you got to use, the edge of your phone, but do use a line when you're graphing. So first of all, if we're going to graph y equals 2, what does that look like?
Horizontal line.
Is it horizontal?
No.
So the y-axis is vertical, so it seems like it should be a vertical line because the y-axis is vertical. But why isn't it? Why is it a horizontal line?
Cross these.
Yeah, it crosses the y-axis at 2. So that line will be a straight line at where y is 2. So these lines, it doesn't matter what x is, y is always 2. So the graph of y equals 2 is a straight horizontal line. I can't move it. Pretend it's exactly on the line. And label it y equals 2. If you want, stick little arrows on the end.
Do you care if we have the arrows or not?
No, I don't care. So let's talk about, first of all, we'll divide this in half because we had 2 different equations, and we'll do y equals 2 in the first half. So it says number of x-intercepts. So how many times will the graph of y equals 2, will it cross the x-axis? Yeah, none. It has 0. X-intercepts. How many y-intercepts does it have? 1. How many turning points does it have? How many times does it change direction? None. And its end behavior, where did it start and where did it end? And remember, it's always left to right. So it started in 2 and it ended up in 1. What's its domain? What are all the possible values of x? So when you look at your graph and remember that this line can go on forever. Yes. Think about all the things that x could be. And in Math 10, we used to talk about the shadow that it creates on the x-axis. So every single ordered pair, what x would it match up with? So domain is, what are all the possible x values? And it can be anything, can't it? That line goes on forever, so it can be every single x that's possible. So we say all real numbers. And you indicate that by saying x can be in the set of all real numbers.
That's Chantal.
Can someone grab the door, please?
I can do that.
Thank you. Now, as we travel along the graph, and remember, x can be anything. While x is anything, what can y be? Y has to be 2. Okay, it's a vertical line. It doesn't go up. I don't have any other shadows on that y-axis. It's only 2. Here. So I would say that the range is y equals 2.
Okay, why do you use the E for what?
In the set of. It says x can be anything. That's what it means. Yeah. All right, go ahead and try x equals -1 yourself. So how many x-intercepts will the line of x equals -1 have?
1.
It just has 1, and I made it blue so you could see. Cuts the x-axis, just like how the other one cut the y-axis. How many y-intercepts? 0. Turning points? End behavior?
2 to 3.
Went from 2 to 3.
How do you not just say 3 to 2?
Because
That one, maybe top to down, just like we went left to right. Yeah, positive to negative. The domain?
x equals -1.
Yeah, all x can be is -1, but y is
Yeah.
in the set of all real values.
Do you have to do the R like that with the 2 like that one?
You can put an R and I would know what you mean.
I've never seen it with 2.
I
Okay.
understand.
All right. If you didn't want to put anything, write the words all real values. Means the same thing. All right, so constant graphs, vertical and horizontal lines. Yes?
I don't know how the lines work.
Because all I know, I don't know anything about y. From the equation, I can't tell anything about y. All I know is x is -1. So you could go to any y you want. Let's say we went to y is 4. Well, I know for sure that x is -1. If I went to y was -4, all I know is x is -1. So no matter what, x is -1. Or you could think of it as a line that cuts the x-axis at -1. Moving on to the second kind, any idea what they are? What type of functions they are? Linear. I have no idea what I did. And they are degree 1, yes. So we've got two variables here. They're in the form of y equals mx plus b. The variable's x, and because there's nothing there, it's a 1. So they have a degree of 1. So we talked about these yesterday. When they're in the form of y equals mx plus b, this is where we begin. That's your y-intercept. And this is how you move. That's your slope. So if we were to graph y equals -2x minus 1, we would go to the y-axis and start at -1. Now the slope says -2, John. What does that mean? How do I
It's
move?
going down.
Yeah,
Go down
as
to
you go from left to right. Okay, so how do you know 1?
Right? Because it's like 2 over 1.
Yeah, that's right. So remember, it's rise over run. And because it's negative, I'm going to go down. So you go down 2 over 1, put your dot down 2 over 1. What else can you do? You can go down 2 and to the right.
Go up 2 and
You
over
can
1.
also go up and to the left. Okay, normally 3 ordered pairs is enough. It's not bad. Label your line with its equation. Y equals -2x minus 1. And go ahead and answer those questions. How many x-intercepts?
1.
Crosses the x-axis 1 time. How many y's?
1.
Just 1. How many turning points? How many times does it change direction?
0.
None. That's what makes it
Linear.
a line, exactly. Its end behavior, it started in?
3.
No. 2.
Oh, wait.
Starts in 2. Ends in 4.
Wait, which one?
Y equals -2x minus 1. Its domain? If I were to generate ordered pairs using a t-chart for the graph of y equals -2x minus 1, and remember you could always do that. You could think of a bunch of x's and then get some y's based on that. Is there anything x couldn't be? So my graph goes on forever, so if you were to trace every single ordered pair towards the x-axis, I could use anything. So it's all real numbers. And then what about my range? Same. Yeah. Because those graphs go on forever, I could always trace towards my y-axis and get a y value. Go ahead and try the other graph.
Why is it going from 2 to 4?
This is
You
2.
go left or
Oh,
right.
that's 2? I thought that was 1.
Nope, 1's here.
Because it's negative on the left side.
Graph your second line of y equals 1/2 x plus 3. Start on the y-axis at 3, up 1, over 2, or down 1, back 2.
Oh my god, it's like half x. It's one of these two?
Yeah.
That's right.
So if I were to extend this graph, even though it looks like it starts in 2, if I were to extend this graph, I'd be in quadrant 3, wouldn't I?
3 to 1, is it?
So I would say the behavior is 3 to 1. Is there anything different about x-intercepts, y-intercepts, or turning points?
No.
Same. So like the very first page said, types of graphs will have the same characteristics. Linear graphs will have the same. Domain and range, same. So, should be review for you, stuff you've seen before. If you want to borrow now a graphing calculator, leave some collateral.
Some big mountain from there in my face. So I was up hardcore when I was there. And then I had a clown face. I was like, well, what am I going to do?
The great thing is, like, when an animal gets on your brush, you're allergic to animals.
Oh,
And then you just rub it all over your face. And
I live with 5 dogs and my makeup brush is dog food. It's not even any other thing anymore. I wasn't going to come to school with like all those.
All right, continuing on to the third type of equations. What are they? Quadratics. What makes them quadratic? Yes, they have the degree number 2. They have a squared on the exponent, on the, I keep saying that, on the variable. Let's graph this one. We kind of call that the default graph, y equals x squared. Let's graph that first. So these are going to be parabolas. Do you remember what they look like? Where would I start on this one? Yeah, I can start at 0 and 0. How do I know I can start at 0 and 0? Because so far I'm at y equals x squared.
0 squared is 0.
It is. That's right. So if I were to graph this function, I could create a table of values. I could pick any x's and then generate some y's. So if I input 0 for x, so if I make this 0, 0 squared is 0, exactly like Cole said. So the ordered pair for 0 is 0 and 0. What is it for 1? 1 and 1. So over and then up. What if I put in negative 1?
You can't
Go down.
What's negative 1 times negative 1? 1. So if I go back 1, I still go up 1. What if I go over 2? What if I make x 2? Nope. It's 4 because 2 squared is 4. So over 2, up 4. Can you see where your vertex is now? 0. Here's your and here's your axis of symmetry if your vertex is there. Remember, parabolas are symmetrical. So once you can visualize where your axis of symmetry is, you don't really have to count squares all the time.
Are we doing the first one? Oh, we're doing x squared.
Yeah. So if we're 2 squares to get to the axis of symmetry, we can put another one 2 over and generate another one. If I went over 3, how much would I count up? 9. So you could eyeball it to be about there. And then you could count 3 squares to your axis of symmetry, count 3 squares over to get the corresponding symmetrical point. You have to freehand these and label, please. Now, do that on your graphing calculator just to make sure you can. We'll be in our y equals screen. Clear out everything that you have. Type in x squared, and then just to make sure you get the standard 10 by 10 window, press zoom, then 6. On your graph, how can you verify that there's an ordered pair at 1 and 1? What are 2 ways on your graph that you could verify that?
Second calc minimum.
What?
Second calc minimum.
No, that's your vertex.
Oh, sorry. Isn't that a point? Go to your table.
You could go to your table. Yeah, you could press second graph to get your table of values. And then you could scroll down and see that when x is 1, so is y, just like we had in our table of values. Press graph again to get back to your graph. What's a faster way? If you're here, why don't you put away your phone and participate? Okay, since you're here. Yes, trace, and then type in 1, enter. And then you will, same with you, put away the phone. Enough. I'm not talking to you. So that's how you can verify that the ordered pair of 1 and 1 is on your graph. How do you verify 2 and 4? Type in 2, and it should snap to 4 with a little cursor on your parabola. All right? Talk about behavior. How many x-intercepts does this particular one have? It has 1. Right at the what? Origin. Not origin. Vertex. How many y-intercepts? 1. How many turning points? 1. What's its start and end behavior? Starts in 2, ends up in 1. What's the domain? Anywhere on that graph, if you stuck your pen anywhere on the graph, and remember that this parabola will continue to go outwards infinitely. Anywhere that you stuck your pen on that graph, can you trace towards any value on your x-axis? Yes. There. So it will be everything. Now think about that graph. If you stick your pen anywhere on that graph and trace towards the y-axis, can the domain be everything? Greater than 0, right? Shh. This is the lowest point that graph will ever go. So we will say that the range y is greater or equal to 0. Because its vertex is right at 0. All right, let's do... we can do y equals x squared plus 1, but just do, let's do it just on our graphing calculator. We don't need to draw it here. We're already kind of busy. What's going to happen, though, when we go and leave y equals x squared on your window? Now go down to y2 and type x squared plus 1. So you're going to have 2 graphs on your window. It's the same graph except for,
It goes up.
say it louder.
Starts at 1.
Yeah, it's the same graph. It just started at 1. I know.
No. That would be a one.
So is the behavior for this graph, the behavior for y equals x squared plus 1, what's the only thing different in terms of its behavior? There's one tiny change. Well, no, there's two. How many x? There's no x-intercepts. That's right. It still has one y, one turning point, 2 to 1. Its domain, everything. However, its range is now
Greater than, equal to or greater than
1. Yeah. Because it's just moved up one spot. Now, based on that, what do you predict for y equals negative x squared
It's going
It's gonna go down.
plus 1? It has to go down because it's negative. That's how it works. Lovely. I'm going to erase all this so you can see something. Go ahead and graph it on your graphing calculator. Make sure that you don't put subtract x squared. You have to put negative x squared in your window. So if we were to rewrite y equals negative x squared plus 1 in vertex form, this one, it would look like this. Y equals negative x plus 0 squared plus 1. That's what it looks like in vertex form. I have nothing behind my x. That's how I know it's plus nothing, plus 0. But it makes a little more sense sometimes to see it written in vertex form. This is how I know it goes down. My vertex, based on my equation, is at
0.
and 1. That's right. Did you look at your graph on your graphing calculator? Is the vertex at 0 and 1? Yeah.
Wait, will you show them how to find the vertex on the calculator?
Yep. Goes down. If I go over 2, I can count down 4. So that one looks like this. How many x-intercepts this time? 2. Crosses the x-axis twice. Y-intercepts. Can it ever be any different for y-intercepts? Can you have 0 y-intercepts? Can you have a graph that looks like this? Like, we can shift these graphs to the left and the right. They don't always have to go over the vertex on the y-axis. What if I have a parabola way over here? Is it sooner or later because it continues to go out? Yes, somewhere it's
What
gonna.
if it went completely sideways?
Then it's not a parabola anymore. Then it's not quadratic. Nope. The square root ones.
Parabolas, like, just go, like, up and down, so they just keep going
Nope.
straight.
Nope. They're always gonna expand. Turning points is the same. What about start and end behavior? Even though I've erased it. Okay.
3 to 4.
So it looks something like that. Yes, it is 3 to 4. So it looks something like that. Yes, 3 to 4. Domain. Every time. I can put anything in, but in this particular one, what can I say about y? Now I have a maximum point, right? I have a maximum at y is 1. Yeah, it's going to be less than. So this time y is less than or equal to 1. So those are all things covered in Math 11. Should all be coming back to you. Hopefully. Now we're going to move into cubic functions. I do not think you've graphed cubic functions before. So we will rely on our graphing calculator quite a bit here. So because these have an exponent of 3, they're cubic. Because the highest exponent or the degree is 3. So let's go ahead and graph y equals x cubed on your graphing calculator. So the graph of y equals x cubed will come up from the third quadrant. It kind of flattens out, and then it goes back up. Oh, dear. So it'll look something like that.
So would it be 2 turning points?
Yes. So this particular graph, the one of y equals x cubed, what can we say about its behavior? How many x-intercepts? Just 1. How many y's? Just 1. Does it make sense that it goes through our graph at 0 and 0?
Yeah.
I can still generate ordered pairs, y equals x cubed. So if I, for my x value, if I put in a 0, 0 cubed still 0. What's this ordered pair right here? Does it go exactly through 1 and 1? If I put x as 1, what's 1 cubed? 1. So I do have an ordered pair at 1 and 1. What's another ordered pair? 2 and 8. So you could kind of draw it over 2, up 8. Can I go back 1? Negative 1? What would negative 1 match up with? Yeah, it would. Because negative 1 cubed is negative 1. Negative 2, negative 8, etc. Okay, number of turning points? 2. So it changes direction here and then there again. Start and end behavior for this graph? 3 and 1. Domain? Everything. Same with range. So because the degree is odd, it's a 3, it's odd, they actually behave quite similarly to linear functions, which also has an odd degree. In the old Math 11 curriculum, we used to go up all the way to degree of 5. And so the 2's and 4's act the same, the 1's, 3's, and 5's relatively act the same. They start and end in the same place and behave sort of similarly. All right, what happens if we, let's do this one. Let's keep our positive a, but let's do this, let's do the last one. X cubed minus 3. What do you think's going to happen? Okay, so let's check it out. So leave x cubed on your graphing calculator, and in y2, put x cubed, and then put subtract, not negative, and then graph it on the same graph. Does it make sense that it's basically the same graph, just down 3? So it will look something like that. It's just down. Same behavior. One x-intercept, one y-intercept, 2 turning points. Start and end in the same place. Domain's the same. Range, same thing. All right, use your graphing calculator to graph the last one, which is the middle one. Negative x cubed plus 1. Erase the other 2 this time. Start fresh. Down, like that. Okay. Does anything about that graph surprise you? Shay, are you okay now? Can I go back up? So that graph crosses the y-axis at 1, right? What's another ordered pair that you can probably predict? Remember how the other ones, if I went over one, I was able to go up one? Can I do that here?
2 and negative 7.
2 and negative 7? Can you verify that on your graphing calculator?
Yeah.
So if you go second table, it generates all the ordered pairs for you. You don't have to. So there's 0 and 0. Sorry, 0 and 1. It also says 1 and 0, so you can put those dots to help guide your sketch, just so you're not completely freehanding it. It says 2 and negative 7. It also says negative 1 and 2, which matches up at this point, doesn't it, after a direction turn? And negative 2 and 9 up there. So it just sort of gives you a bit of a guide when you sketch. It's not going to go straight down, it's going to go outwards. So it'll look kind of like that. So if you do have to graph or sketch these, use that table of values to help you and get some points that can guide.
Graphing paper for the test.
You, no, not for the test. X-intercepts, is there anything different here? And remember, this is going to be like the linear functions too. It still changes direction twice. The only difference is the end behavior. Why is that? Because now it's 2 to 4. Not 3 to 1. Why? Why is it going down? Because it's negative. This changes where it starts and ends. Okay? Domain and range, any differences? No. All right, last 2 questions and we are done. Have a look at those 2 graphs below. It says determine which of the 2 do you think could represent a polynomial function.
A.
What is a polynomial function?
What isn't it?
So what does this look like? What does A look like?
Quadratic.
It's a quadratic. How do you know? Like what?
It's not parabola. It's got a minimum.
How do you know? Okay, it's got a minimum. It's got 1 turning point. I heard it over there. That's the minimum. What else? How do you know? It does cross the x-axis 2
That
times.
doesn't mean it's a quadratic.
Yeah. It's symmetrical, right? Yeah. Yeah, so we can say this one is. What about B? Goes from 2 to 1.
It's linear.
How many turning points does it have? It's got 6 turning points.
What would that be?
Sinusoidal. It's a sine graph. So no, not polynomial.
Why not?
It does not behave like the 4 that we covered.
This doesn't look like it.
Yeah,
So polynomial
That's discrimination.
the 4 that we covered.
Matthew's doing those. It's pi.
Yeah.
You're doing pi. And I'm like, how
Yeah.
do you graph pi?
You don't graph it on a quadratic plane, you graph it on a
Yeah.
different kind of graph. All right, you need to be able to do the 2 questions on page 383. You're responsible for knowing how to do question 1 and 3.
That's it?
Quiz tomorrow.